Now, last day we were talking about this thought experiment by Faraday, and you remember we had copper rails hooked to a light, and between the rails we had a uniform magnetic field that was generated somehow. We had a copper bar that was free to slide on those rails. And we found that if we took our hand and pushed the bar along the rails, that we got a current going through the bulb. Now, we could explain this current because moving the bar was moving the charge carriers. We were moving charges this way towards the open door in a magnetic field that way, and that pushed the current up the bar. And once it started flowing up the bar, what goes around comes around. Now, here's the thing. We learned in 205 that once something gets moving, it wants to keep moving. That was Newton's first law. A body in motion stays in motion. So if I could get rid of the friction between these copper rails and that bar, all I would have to do is just get the bar moving. If those rails were long enough, I could just have free energy the rest of my life. Free energy. When someone tells you you're going to get free energy, what do you wonder? Yeah, what's the catch? What's the catch? And what we find is that as you're pushing this rail, as soon as you let go, instead of just keeping going forever, it grinds to a halt immediately. Just, okay? And here's why. This current, or this motion, was caused by a magnetic force. My hand was pushing the charges this way in a field, and the magnetic force pushed the charges up that bar. But once the charges are moving up that bar, that's another motion in a magnetic field. And if they're moving that way, in a magnetic field that's that way, that gives me another magnetic force that's going to point that way, by right-hand rule number 1. And that will fight the motion. So that if I want to keep that bulb lit, I have to continually push with my hand, always overcoming that magnetic force, and that means I have to be doing positive Vary. That's where the light's coming from. That's where the energy's coming from. It's not free. Now we can use that same principle to develop what are called magnetic brakes. I have here a copper ring, and I'm going to swing that between the poles of this horseshoe magnet, and you see that it very quickly just stops. Now, if I were to put that in liquid nitrogen and cool it down, it would stop even faster. I have here another ring. The people in front will testify that it has a cut in it, right? Okay, you'll be my witnesses. Okay, and in this case, I can't get any induced current set up, and so it just keeps on going. Okay? Now let me explain that. If I just had a copper sheet swinging down, and what are these X's right here? Yeah, these are the magnetic field lines that are going away from you. Okay? So you've got a north pole near you, there's a south pole away from you, and the field lines are going from north to south. Now, I can think of this sheet of copper as a whole bunch of copper loops, one inside the other. And as I move that copper sheet through the magnetic field, I'm changing the number of field lines that are passing through. Well, let's just pick a copper loop, that copper loop there. As this swings through, did you hear that? Did you hear that? That's the crescendo. Oh, I love that. Okay. Now, as this is swinging down I'm changing the number of field lines through this copper loop from none to some into the board. Fight that change. I'm going from no field lines into the board to some field lines into the board. Which way do I send field lines? Out of the board. Out of the board. Do it with your right thumb every single time. Out of the board. And that means the current has to flow counterclockwise by right-hand rule number 3. Now what I care about is what's the current doing right here where it's acted on by the magnetic field. Well, right there it's going up, and that's current in a magnetic field into the board. That gives me a magnetic force that fights the motion. Fights the motion. Now let me show you that. I've got a bar of copper, and if I put that on here, okay, it slows right down. Now if I take a bar of copper and I turn it into a cone, I've got cuts here so that I can't get any current loops. In that case, predict what's going to happen. Yeah, if I can't get any induced current loops, I don't have any magnetic force and there's no braking. Now this is going to be cold. Okay. I got 10 fingers, I can spare a few. Oh, come on. I can do this. Okay. Watch what happens now. Okay. Imagine you're using magnetic brakes on your bullet train, and their bullet train over in Japan just made a new record, 375 miles an hour. That's faster than my car will go. And suppose they do the magnetic brakes and someone says, hey, you know, we cool those down for you. And then we come to the next stop, next station. We're stopped. Everyone's right up at the front of the train. Yeah. Okay.